Okay, so as promised, say a few words about these equations. And just wanted to reiterate that this lab is actually a lot more interesting than my first impression, because we're gonna come up with an equation for the work right here. And if you remember, at the beginning of class, I was a little herky-jerky about with the concepts, because I thought we needed to count the number of times that we wrapped the rope around, but it turns out that it doesn't matter, because I was thinking about friction and the amount of force that the rope is pressed against the cylinder or something like that. But I began to realize that that's not critical. The number of turns of rope, there is a critical part, but I'll get to it in a minute. And so, yeah, I forgot we have our paint can here. So we have some W force, the weight, and then there's some upward force, the tension in the rope. And so let's see what we got here. Now, in general, we've learned that work equals a force times some distance. And so if we have some object and it moves a certain distance to the right and the force is pointed in the same direction, then we say W is positive. And you can also have a situation where the object is moving this way still, but somehow the force is in this direction. And that's actually not so hard to understand, because it could be friction, for example. So this work is less than 0. And we also know that if S equals 0, then work equals 0. So the weird thing is that I better get myself ready with some more space just in case, is that we're claiming work is happening, but the can here is not moving up or down. So even though I could say that one of these two forces is doing positive work and the other one is doing negative work, since the can is not supposed to move up or down, what's going on here? So let's start off by talking about what is torque, because we have something rotating. So torque is called twisting force. And so the simplest definition is that if we have some force times a radius, the distance away from the center of the thing that's rotating, then that is a torque. And if you think about, if you need to use a wrench to pull off a bolt, that the longer is the wrench, the easier it is to remove the bolt. And that's why when you go to bigger bolts, you get the wrenches are longer, because in general, bigger bolts are tightened more than smaller bolts. All right, so and we know this is our drum. It rotates around here. So in this case, the force happens to be W, and it's exerting some kind of torque. Okay, that's great, but where is the S going on here? And in this case, what the S is the fact that the rope is slipping past the drum, and we have to we have to put our own torque into it. We have to twist the drum. And so what the weight is trying to do is trying to twist this thing clockwise, and we turn the crank, and in this illustration, we need to turn it counterclockwise. So we're exerting a torque, and that torque is doing work, because we can measure it, because we can say, oh, the drum is slipping past the rope, or I'm turning this thing round and round. And so the amount of work I've done is how many times I've turned it around, and I need it, but that's an angle, and I need to turn it into a distance. So, oh, well, I know that the distance around is 2 pi r, and the number of times I crank it is the total distance it goes. So now we can see how, so we have some force, and that happens to be W, and then, which is equal to mg. And so and then we're applying that force over this distance, mg 2 pi rn. And that's a slightly different way than what the book talks about, the manual. And what happens here is that, so I'm sort of mixing apples and oranges, because I talked about a twisting force, but I related it to a kind of distance around the cylinder, so I kind of cheated a little bit. But remember then, if I have a force times a distance, when I go in rotation, we have distance for what this is called translation, when I move along somewhere. And when I rotate, the analog to that is theta, number of radians. And just to keep going, speed, and then that's omega. That's how many radians per second. And then acceleration is equal to alpha. So how many radians per second squared? And so how much faster am I going every second? So anyways, in this case then, if I exert a torque, then this sort of twisting force, the distance is theta. So then I say, okay, I'm going to, for work, and just as you see above, is the torque times theta. And as I said, the torque is equal to some force times r. And so that is the W once again, which is equal to mg. So that means that, and careful, this is capital W, and this is little w for weight. So now that just is mgr. That's what torque is. And then how many radians total in our case? Well, that just happens to be the circumference times 2, which is 2 pi, times the number of times we crank it around. So we get the same answer. And it's pretty darn interesting. And I mean, remember I was thinking about the other end of the rope, and so I was thinking that maybe we could have tied it on to something. So what would happen? We'd still need to have this thing hanging here. And I think that if we tied it on to something, we could set it up so it was hanging, but it was not turning, and the other end is tied to something. And it seems to me that we could start turning this around. And I think what we'd notice at first is that the can would start lifting. And then, of course, this rope would start to become slack, so then the amount of friction between the rope and the cylinder would go down, because now I've got a tension here and a tension there pulling on the rope. And as they started turning, this tension would go down. And I'm wondering, well, let's see. This is, neither. If in the short form, that's neither here nor there. In order for this formula to hold true, we need to make sure that the only thing exerting a pull here is W. And we do that. What we did is we held this end with our hand, and we made sure that there was no force pulling on this end. It's just that my thought was that if we tied this end, then we had to determine how many times to wrap it around the drum. But again, I'm sorry to free associate. I've just had some thoughts. But the one thing you have to make sure that you describe is that you wanted to make sure that you had no force here. And one could imagine that if I have a force there, that means that the torque is being created by this force, and we don't want that to be true. We want the torque and the twisting force that we have to exert to be only because of this, the weight here. So that means the end of the string has to basically be limp. That means that the person holding it doesn't feel any force. That's the important point. And then, but that, to me, again, that's so cool, because it doesn't matter about the friction, but the friction is also causing the heat. But we don't have to know any details about, because remember, friction is the how hard something is pushing against the other thing. All right, the normal force times some coefficient. Well, if you think about it for a minute, if I wind this rope around the drum, the rope that is right as it touches, that's going to be pushed against the drum the most. And then remember, if this end of the rope is limp, that means that it's not being pushed against the drum hardly at all. So the amount of friction force along the rope is not constant. So it's a pretty complicated calculation if I really wanted to know. But the way this thing is set up, I don't have to know that. I just know that I'm cranking this thing. I have to exert a certain amount of twisting force to keep the can off the ground, but not moving up or down. And then that's the amount of work that I do on turning the crank. So I'm adding that work into the system. And lo and behold, when I do that, this relationship here, the J formula, it says basically that I'm going to put so many Qs into the system, or in this case, joules per calories, but I can invert that. So that would mean that I would expect a certain amount of temperature change. Well, forgetting this formula for a minute, if I notice the temperature is changing, then if I know the specific heat and the mass, then I can tell you how many calories of heat were put into the system. And the thing I think is pretty heavy duty is that work divided by Q is always the same amount. But in this case, we know it's friction putting in the heat, but we don't know we really ignore all of the details about the friction. We just couch it in these terms of the work we put into the system. And then the work we put into the system gets us a fixed amount of Q in this ratio here. And we measure the Q independently by measuring the temperature change. I mean, that's just a trip. I think that's pretty heavy duty. And just to finish everything, remember we have to do D1 and D2. So we have D1 is the, well, I don't remember off the top of my head, but it's not critical which is which. One of them is the diameter from the outside edge of the rope to the other outside edge. And then the D2 is from the edge of it's the diameter of the cylinder itself. Because at the end of the day, we want R equal to here. And remember, when I have these two dimensions, then the average value, the point that's halfway in between, is going to be D1 plus D2 over 2. So that gets us D average. Of course, we need to get radius. So we want the average radius. So that's just equal to average diameter divided by 2. And so notice that if I then say that D bar is equal to that, then I say D1 plus D2 divided by 2 divided by 2 equals D1 plus D2 divided by 4. That's all. Pretty straightforward. Okay, and then don't forget you have your spreadsheet with your column of resistances, and you have to enter that into your spreadsheet. Excuse me. And it's actually not super hard, but well, let's see. I can do it here. I can show you, but you got to remember that I don't have any R values, right? So let's paste that here. Right, so let's say this is our column of R values, and and remember R has to be in ohms. So if we said it was, we read off 10 kilo ohms, so that's R in K ohms. We need to get R in ohms. And so R in ohms, and that equals to this times 10 to the third, which is 1,000. So that means I had 10 kilo ohms is 10,000 ohms. So then what's T? And so I just had a burst of inspiration. And so that does get a little, that's the JPEG. When you get noise added when you do the compression. So this is a toughie, so let's go through it. Equals, it's a tedious one really, 66.314 minus you know what, let's make our lives easier. I just had another inspiration. Let's get out of this for a minute. So we'll put these numbers somewhere. So we have 66.314 6.621, and that's E minus 4, and 3.045 E minus 9, and enter, and the last one is 5.62. Oh, who cares about 10 to the minus 15? Jesus. 5.62. But let's just do it all by the numbers. Minus 15. And then I left a space there. So I put a space. That's a boo-boo. There we go. There's our numbers. We can get clever here. And we can turn them into, let's say, scientific notation. Ooh, we're all happy. So then T is going to equal the first one. Don't forget your F4 because you have to fill in. And then it's minus the second one, F4 times R in ohms. And then what's next? Plus the third one times, F4 times R in ohms. But we need to square it, so a little caret, shift 6. And then it's minus the, what happens if I can't get to it? Okay, so let's get rid of that minus sign for a minute. So we'll just leave that there. How am I going to make this work? I know. If I was zoomed out, it wouldn't be as much of a problem, but I'm just going to make it quick and dirty. And I'll just paste. So let's double check. Did it remember? Yep. So it moved. W22 is here. W23. So now I just have to add the last. So I just double click there. Or excuse me. So if I double click here, then I can put the cursor is in there. So now I just have to say minus the last one times, this is going off your screen, times R, excuse me, we need the F4 key, times, and let's see if we can make a recovery here, yep, R cubed. Okay, so that's the resistance, and then the caret times 3 cubed. Well, raised to the third power. And so I don't have other ohm. Let's say then 10. Let's see, 10.3. And I don't know, 10.7. I'm just making it up off the top of my head, guys. And so then I fill in the amount of kilo ohms, and then I can fill in the temperature, and there you go. And in this case, you might want to, you don't need scientific notation here. I would make them numbers, so there you go. So they're actually not outrageous. Let's see. If I say that's 25 plus room temperature is 25, so this is about 60, so that's 35 degrees above room temperature. That's a bit much. So we know that if in this case, let's say 20 kiloohms, temperature went down, 30. So we want to say 15 degrees above, so that's 25 plus 40. So let's try making this 40 kiloohms just for the fun of it. So we're almost there, 45. So now we're close to 15 degrees above room temperature. So that's a little bit more realistic. Isn't that interesting? R in kiloohms, but that's just a coincidence because if we're going to cool down, we know that we've noticed that the resistance is going to go up, not down. So let's make this 46. Yeah, so the temperature is going down, but the resistance is going up. 47. So now we're getting more realistic looking temperature numbers. And I don't remember what people's kiloohms were, but anyways, there it is. So have fun. See you later.